UV visible spectroscopy that we have already completed halfway. So today I will finish it, and IR spectroscopy also. Both the way halfway done. Okay, some IR spectroscopy, some UV spectroscopy is completed, but the rest part I am continuing. So spectroscopy already I have introduced to you that what is spectroscopy? The matter energy interaction. Okay, the interaction between the matter energy gives a sort of that analytical some diagram, and it is plotted into some plotter. We call it spectrum. Now this is the overall plan, that how do you do the spectroscopy. You have a light source, you have a collimator that will focus the light into a beam, single beam, passing through prism, and then it is passing through slit. Okay, and this, what is the purpose of prism? Prism is diversifying the light. Prism is actually forming a spectrum plan. It is forming a spectrum. Spectrum means different colored light. Different colored light. Now through a slit we will collect only one beam. Let it be green, let it be yellow, only one beam. And then it is further filtered into a single wavelength, passing through sample holder containing the sample solution, and finally going to detector. Okay, so this is the overall scheme or plan for UV visible. Now what is the ranges of UV? 185 to 400 nanometer, that is called UV. Visible is 400 to 800 nanometer. These two are the major constants here, because we are discussing the UV visible spectrophotometry. So UV region is 185 to 400, visible region is 400 to 800 nanometer. Now this is called actually the electromagnetic radiation. We know this term is very common to us. Light is a electromagnetic radiation. Okay, light is a form of electromagnetic radiation. What is electromagnetic radiation? Electric field and magnetic field both are propagating together and perpendicular to each other. If one is the electric field, see the red one, the other one is the magnetic field, the blue one. So electric and magnetic field both propagating together, we call it electromagnetic radiation. So light is electromagnetic radiation. Now wavelength, these are some basic idea that you get from much from 9th and standard itself, that we know these things, that E equal to H nu, okay, nu lambda equal to C. Okay, so those relationships you have to recap once more. Wavelength is lambda and nu lambda equal to C. So energy directly proportional to frequency and inversely proportional to wavelength. This type of ideas, basic things. Now going to the next part, the interaction of electromagnetic radiation with matter, and that we are getting the spectrum. Now when a photon of energy h nu bombarded to a particular molecule, maybe, okay, so then the electronic promotion or transition take place. So electronic transition from ground state to some extra state. So maybe from 0th level to nth level. So that sort of transition. Different type of transition possible. Electronic transition. That Lyman, Balmer, Paschen, bracket, Fund series. They are all different sorts of electronic transitions only. Ground state to first level, ground state to second level, ground state to third level. That is giving us one series that is called Lyman. First level to second level, first to third, first to fourth. That way you get another series called Balmer. So Lyman is in the Lyman. Why I am talking about that? Because these are very well known to you. So Lyman series, it is in the ultraviolet region, Balmer in the visible region. So these are the actually first time we introduce. You already introduced to spectroscopy. You know the spectrum. You already know about the spectrum. Now you are learning a bit detail for practical purpose. Okay. So atomic spectrum is only theoretical aspect. Practically implication is less, but here this spectroscopy you are using for different analysis of samples, sample analysis, for a different purpose altogether. You have got some water, and you have got some doubt that this water contains some drug. How do you decide whether there is a drug mixed in the water? Some white color particles are floating in the water. Maybe you have got some doubt. So whether really forensic test, really there is some drug or not, How do you decide? With spectroscopy. With the help of spectroscopy, you can actually decide whether there is a drug mixed into that water. Okay. So this is the practical thing. Now we have different type of energy levels associated with electronic transition. One is vibrational spectrum. So vibration is associated with different electronic levels. Every electronic vibrational level is associated with so many rotational levels. Rotational energy requirement is very small. Vibrational energy requirement is something more, and electronic transition energy requirement is very high. So electronic transition, that is falling in the ultraviolet and visible, because energy requirement is very large. Okay, so these are called different energy levels, ground state, excited state, all these things, these terms we are using. So different energy levels. In each and every electronic energy level, there are so many vibrational level associated. Okay, because so many vibration possible for a molecule. Every electronic transition is associated with so many vibrational levels. Each and every vibration level associated with so many rotational levels. Rotational energy is very small. That is microwave range, falling in the microwave category. Long wavelength. Then heat is actually microwave. So that is long wavelength. Okay, microwave oven, that we are using actually microwave to heat the food, reheating of food. The molecules, they are associated with the food material. These are always rotating, but if you give some more microwave energy, they will be rotating much faster. And by that rotation only, they are knocking each other, and the whole energy is getting dissipated to the food, and the food is getting heated up. That is the technology, nothing else. So that means what I mean to say, there is electronic levels. Every electronic levels we have some vibrational levels. Every vibrational level we have some number of rotational levels. Finer aspects, big energy gap. Okay, first level, second level, third level, the energy gap is quite large. Then into every energy level, there is associated some sub-levels. They are vibrational levels. Now each and every vibrational level, you have some rotational levels associated. It is a finer one. In this vibrational level, there are some rotational levels there. They are very closely spaced. Gap is very small. It is the microwave range. Then IR. Okay, which one? For vibration associated to IR frequency, and transition related to ultraviolet. Mostly ultraviolet and visible. Ultraviolet and visible radiation giving the transitions, electronic transitions. That's why color and all these things, property we are getting from electronic transition only. And then which one, the different type of molecule are there in the atmosphere, which molecule will absorb sunlight and responsible for global warming, that is related to vibration. That is related to IR, vibration. Okay, it is not related to any ultraviolet, but it is related to vibration, and that means infrared radiation. Okay. Now after that, the dissipated energy is giving heat. It is converted to microwave. That's why. When you take a glass made room, the sunlight is penetrating through the glass. When it falling on the glass, it is UV visible both. When it is passing through the glass, after that it is converted to IR and microwave. Why? Because small short wavelength converted to long wavelength. Why? Because it is some amount of energy is already absorbed. So the intensity, the energy that is entering the glass material is reduced. Energy is reduced, not intensity. Energy is reduced. What is the difference between intensity and energy? Energy associated to a single photon. This particular photon has got this much of energy, h nu. Another photon has got another h nu. Nu is different. Okay. So, but intensity, how many number of photon is knocking on a particular surface or a particular area, surface area per second. Number of photon bombarded into a particular area per second. That is your intensity. And energy that is h nu. A particular photon carrying how much energy? That is h nu. And what is the nu? Frequency. Okay. So every the particular radiation will have a different frequency and different energy. So energy and intensity are different. Intensity means number of photon bombarded to a particular area. Unit area. Unit area, how many number of photon is bombarding, that is called intensity. And what is the energy? Energy associated to single photon, every photon. Ultraviolet, you have very high energy. So every ultraviolet radiation, light, you have a high energy. But someone will have a higher, someone will have a comparatively lower. But all are high. Got me? Could you understand? Now you have visible. In this visible region, all are high energy. We can call them all of high energy. Yellow is high energy, red is high energy, blue is high energy. But you can obviously decide which one is higher. Blue energy is higher compared to red. Higher energy, I mean to say. So every photon has got in that range, the energy within certain range. Energy within certain range. But intensity, how much light? Okay. That's a different phenomenon. Now, electronic transition, sigma star, for example. This is one possible electronic transition. It will be a maximum energy required for this type of transition, sigma to sigma star. Energy requirement will be very high, so usually it will fall into ultraviolet or visible.
But sir, how do you get the sequence of?
No, that molecule to molecule it will vary. For not for any molecule. Generalize you cannot do. Specifically for every molecule you have to decide how much is the energy requirement, and how to do that? By measurement, actual measurement. You cannot predict without testing that this will be the value. So these wavelength values, those who are given, these values are actually tested values. These tested values. Rotational energy is very small. It is falling in the microwave. Okay, vibrational energy is comparatively higher. It is falling in the IR, infrared. And electronic transition energy is highest. It is falling in the either ultraviolet or visible. And what is ultraviolet range? Ultraviolet range is usually 200 to 400 is ultraviolet. And 400 above, longer wavelength compared to 400, that is visible. 400 to 800 visible. But sometimes we can go beyond that also. If your machine permits, you can go up to 11,000. Okay, triple G. Okay, instead of 8,000, you can go up to 11,000 also. So, N sigma star transition, requirement of energy is comparatively less. N sigma star is quite easy and probable transition. Sigma star is very difficult because it will require very high energy. And if any high energy transition occurs also, that electron will come back also quite easily, because that is very high energy state. It cannot stay back that time for a long period. So usually it comes back very, very fast. But N to sigma star, it is comparatively easier transition because energy requirement is smaller. Now pi to pi star, this transition supposed to be very small energy transition. But pi to pi star transition, we don't expect much. It is forbidden. Why? Because symmetry is opposite. Same symmetry we will prefer. Okay, will be preferred. Same symmetry. Orbital has got symmetry. All the orbitals are having some certain symmetry. So now I will highlight what is the lights into the area, that what is symmetry. You have S orbital, spherically symmetric. That term you have already heard. That S orbital is spherically symmetric. As it is spherical, it is symmetric. But if it is not spherical, suppose dumbbell, upper portion you have one lobe and lower portion you have another lobe. The upper portion usually designated by plus and the bottom portion we put some minus sign. Why? Because it is above the Cartesian and below the Cartesian. So that means it is opposite phase. Upper one is plus phase and bottom one is minus phase. So that means not same phase. So that's why from the center if you draw a line, upper and bottom, so upper and lower, if you draw a line through the center, upper you are getting plus and lower you are getting minus. So in that case it is not symmetric because not same phase, opposite phase. So p orbital is not symmetric. We can call it U, ungarried. That means asymmetric, not symmetric. And what about S? It is G, garried. Okay. So this is called symmetry, concept of symmetry. So S orbital is G, means garried, means symmetric, and p orbital is U, is ungarried, asymmetric. Got the idea? So some basic idea.
P টা কেন হলো না বলতে?
Plus and minus. Plus phase, minus phase. Dumbbell too. Center you have a nucleus. Plus above the Cartesian, minus is below the Cartesian. So above the Cartesian is plus considered plus, and below the Cartesian considered minus. Opposite phase. That's why symmetry is not there. So we have the rule is from the center you have to draw line. Equal distance, if you get the same phase, it is symmetric. If you don't get the same phase, it is asymmetric. So that's why s orbital is symmetric, but p orbital is asymmetric. D orbital is again symmetric, because plus minus minus. 4 lobes are there. 4 lobes, you have plus opposite, minus opposite. So from the center if you draw a line, minus and minus you are getting, plus and plus you are getting. So it is also symmetric. That means D will be G. So S is G, P is U, D is Z once again. So that way it is called symmetry element. Now if the pi you consider, pi is U and pi star is G. By the same reason, same way, if you consider pi and pi star, pi is U and pi star is Z. Sigma is Z, sigma star is U. Usually becomes opposite. Whenever you are taking bonding and anti-bonding, bonding is found to be symmetric for sigma. Sigma bonding is symmetric, so sigma is Z and sigma star is U, but pi is U, so pi star is Z. So it is opposite symmetry. That's why there is absorption, but it's called forbidden transition. So in pi star transition, these are the all types of transition possible into a chart: sigma to sigma star, and n to sigma star, pi to pi star, and n to pi star. N to pi star can easily occur because there is no problem of symmetry. There is no symmetry problem because n is not neither symmetric nor asymmetric. It is not considered that way. But pi star is what? Symmetric. So that is Z. Pi star is Z. Pi is U. So pi star is Z. So n to pi star, it is quite possible for probable transition. N to sigma star is also probable transition. But pi to pi star, though it is looking quite feasible, but it is called forbidden because of opposite symmetry. Sigma to sigma star also can happen, but it will require very high energy. Achha. Now, these were the things last day I was discussing, and towards the end, if you remember. Chromophore and auxochrome. What is chromophore? Some of the functional groups attached to a molecule giving color. The molecule becomes colorful because of these groups. Like benzene is colorless, but if you put some nitro group, it is called nitrobenzene, it is yellow color. Not yellow orange type of color, okay? Orange type of color. Now, if you have, if you put some other group like NH2, the color is changed. That means these particular groups, NO2, NH2, CN, they can put certain color. Why or how? Because the transition is becoming feasible now. If you have NO2, the NO2 means there is a double bond there, and NO2, these groups are containing some double bonds. Double bond means there is a lone pair also available. Above oxygen there is a lone pair also. So lone pair available, double bond available means pi star all are available. So different energy levels are available. So if energy levels are available, then only transition is feasible and it is occurring. And these transitions, some of them are falling in the visible range. That's why you are getting color. But beforehand, suppose benzene, pi star available. But I already told you pi and pi star transition is very limited. Why? Because forbidden transition. As there is no symmetry, pi and pi star are opposite symmetry, so transition is very limited, not happening. And as a result, it is colorless. Got it? It is colorless. So there is a reason behind everything. Means color, this is colorful, this is colorless. Why? The reason is there. So benzene is colorless. Now, water is colorless. Last day I told you why water is colorless. The electronic transition possible is only n to sigma star and sigma to sigma star. There is no other possibility. Because pi bond is not available. Into water molecule H2O, is there any pi bond? No pi bond. So what are the transition possible? N to sigma star or sigma to sigma star. Both are falling in the ultraviolet region. very high energy, and that's why it is colorless. Water is colorless. So for the same reason, benzene is also colorless. Sufficient electronic transition is not happening in the visible range. Now, if you put certain group into that, the compound is becoming colorful. So that group is called chromophore. That is imparting certain color. Chrome means color. So their particular group is giving color to the molecule. That's what is chromophore. Now, oxochrome, that is helping. Oxo means something auxiliary, something extra. So oxochrome is also giving some color. It is changing the color. Itself not giving the color, but it is changing the color. It has no property that it can directly give color to the molecule, but it is helping to change the color. Suppose you have some chromophore, then you have some oxochrome also. The position of the color will, the intensity as well as the color itself will get changed. Suppose one is yellow, then another will become red or orange. So some color is getting changed because of these groups. They are called oxochrome. So chromophore groups listed here, oxochrome groups like here, benzene and phenol as example given, oxochrome. Benzene and phenol both are actually colorless. Benzene is colorless, phenol is also colorless. But there is some changes. It does not mean that always it will give color. Directly if you give oxochrome, put some certain oxochrome group into ring or some molecule, it does not mean it will give color. But there is some shift. Shift happened. Just check. Benzene is lambda max value 255, whereas phenol 270. So there is a change. 15 unit change. But that change may not give color. So oxochrome group will give color if it is already colorful. That means that. If it is not colorful, it may not give color. But aniline, yes, you see, aniline, it is colorful. It is 280, it has got color. Now, if you are shifting towards more and more towards longer wavelength, there is from UV, starting from UV, you are going towards the longer and longer wavelength, there is every chance that it will give color. It will fall into visible. You are shifting, na? Ultraviolet to visible, towards visible you are shifting. So that means that here benzene 255, then phenol 270, aniline 280, shifting towards more and more longer wavelength. So it will give color. Certain color is there. For aniline also there is certain color. It is not colorless. Now bathochromic and hypsochromic shift I was discussing last day. With the diagram I think it will be easier for you to understand. See the diagram here. So first of all, what is lambda max? Anybody can say what is lambda max? Lambda is wavelength. What is lambda max? That is the wavelength where the intensity of absorption is maximum. In other region also, within a region, there can be absorption. But at that particular wavelength, the absorption is maximum. That is called lambda max. Suppose the absorption started from a region 400. And up to 200 you have scanned and found that 400 to 200 in this range you have got one peak. But which position you have the best peak, highest peak? Maybe it is 197.42. Particular wavelength, 0.42 you can ignore actually. So that comes because when you make a plot and from the plot you are finding out, some fraction may come out, but that is meaningless. So wavelength cannot be broken. So that's why we will take the round value. Like recently I was scanning with some papaya juice and found the peak is around that value I told you, 197.6 lambda max. That means I have got a plot like this here as we have in the board. So the maximum intensity of absorption, that is lambda max. In other region also there is wavelength absorption. Okay, absorption is a wide one, wide peak I have got. Okay, that means there is a absorption starting from here and then going up means what? More and more and more absorption. But when it is maximum, that is lambda max. Got the idea of lambda max? So every molecule having a particular lambda max will give us the idea about the molecule. Okay, that means if you get similar two graphs, plots, one is known, another is unknown solution, you can guess that what solution it is from the peak itself. Position and of the two, one is standard, another is unknown. You have got certain standard peaks which is available in the internet. Now you got some unknown solution, scan. If you take the plot and compare with the available data in the internet, we can guess that what type of compound is possible to be present. So particularly this ultraviolet spectroscopy is utilized to find out the impurity in the drug sample. Medicine, okay, presence of impurity in the drug sample. Nowadays we know the contaminated drug is very common in the market. We are sometimes going for alternative drug, cheaper medicine like Platinum RX, that company, they are claiming that they are giving at a cheaper price. Some are telling, okay, generic medicine. Then what is the difference? If you take some branded company, then impurity percentage will be much lesser. And if you take some non-branded company which is called as alternative, you get a much cheaper price, maybe half price or maybe 1/3 price. But in that case, your medicinal impurity can be very high and it can impact your body. Unknowingly, you are not supposed to use any alternative medicine without any doctor's suggestion. Because it can have, as it is non-branded, there is no guarantee what is there. You cannot test it, isn't it? So that is the problem. People are telling about alternative medicine, people are telling about, okay, you can get much cheaper price, why you are buying from branded one. Branded means it is 100% certified and non-branded means no guarantee. Just like taking loose mustard oil and packaged mustard oil. What is the one is telling certifying, okay, my mustard oil may not be the best, but at least it has got certain quality. But open, there is no guarantee. So medicine is much more dangerous. In case of medicine, you cannot take chances. That's the problem. Okay. So here, bathochromic see this peak you understood. Now, if it is shift is towards the left, it is called blue shift. Means towards shorter wavelength, higher energy. That is called blue shift. Why? Because blue light, you must know, it is much higher energy compared to red light. So if it is a shift towards the higher energy, you can call it blue shift, and if the shift is towards the lower energy, you can call it red shift. This blue shift is also called hypsochromic shift. The term you should know because it is not, there is no guarantee always the blue shift, red shift term will be used. So blue shift or hypsochromic shift and red shift or bathochromic shift. Sometimes what happens? Bathochromic means red shift.
No, sir, batho or batho?
Batho, B-A-T-H-O. লেখা আছে? আচ্ছা. So now this red shift, blue shift, apart from that, sometimes intensity of the peak increases, rises because of some oxochrome also. Intensity may rise. Intensity of absorption rises. No shifting, left right no shifting, but upward shift. More absorption happen. Same everything, but more absorption happened. That is called hyperchromic shift. Peak got higher. Sometimes it got lower. It is called hypochromic shift. Hyper means more, hypo means less. That you know. So hyperchromic shift, hypochromic shift. Up and down. Left, right, blue shift, red shift. Or hypsochromic and bathochromic. This shift, could you follow the shift? This is a very simple area. You can easily understand, you can easily answer. Everything you cannot answer, I am telling you, because this is the beginning. You are just learning first time. Very difficult for you. So that's why I am telling this is the area where you can give your attention. Easily you can answer. So, one example. There is a consecutive double bond, alternative double bond. What is that called? Conjugated. Remember? Conjugated double bond. If there is a more and more conjugation of the double bond, there will be red shift. These are some common things you should know. If there is a lone pair attached, resonance will occur, there will be red shift. Any sort of resonance phenomena will give red shift. If you have alkyl group attached, then also there will be red shift. Got me or not? If you have any double bond, conjugate double bond, lone pair, then also you get shift towards lower or longer wavelength. Lower energy, longer wavelength. That is called redshift. So redshift will occur when there is a conjugation. Got it? Resonance or conjugation will give you redshift. Some of the group can give you blue shift. Which one? Minus I groups. Minus I group will give you blue shift. Plus I group will give you red shift. Opposite effect. One is withdrawing electron and is giving electron. Which one is giving electron will give you red shift. Anything that is attracting electron, withdrawing electron will give you blue shift. This is a common rule. But how much shift will be there, we cannot announce from the beginning. You have to see which group is attached. Depending on the nature of the group, the capacity, the value will change. Sometimes 10 unit, sometimes 5 unit in the nanometer scale. Nanometer scale, all are NM, nanometer scale. So in the nanometer scale, there is 10 unit, 5 unit changes. Now, this thing theory also I have discussed earlier. It is called Lambert-Beer's law. So this is the basic principle based on which is all spectroscopy, particularly ultraviolet and IR, all are based on that principle. It is called Lambert-Beer's law. Polarimeter. What is polarimeter? Optical rotation measurement. So that instrument also, so whether spectroscopic instrument, polarimeter for optical rotation measurement, everywhere this principle is applied. That is called Lambert-Beer's law. What is the principle? Very simple. If you have concentration of the solution higher, there will be more absorption. If you have a thickness of the cuvette longer, that means path length of the cuvette is longer, then also your absorption will be more. Other condition fixed. Only these parameters you are changing. If you can change all parameters together, you cannot understand anything. You have to always change one parameter to understand the effect. So you are changing first the concentration of the solution, then intensity always increases. You have taken cuvette. In this cuvette, you have added 10 microliter solution sample. You got certain peak. You want more higher peak, you add some 10 microliter more, you get higher peak. Quite natural. Same thing, same solution, but you have added something more. That means higher concentration. So that actually we do, practically we do. First I add some 10 microliter, take the peak. Then it's not satisfactory, very low. I'm not happy. Then add another 10 microliter. Then you will find, okay, this much of peak I have got. See, should be some result, should be presentable result. Na? If it is very small peak, how can you people will understand? So some better peak will require, okay, add some more, you get some more peak. So that's why trial you have to take. In one trial you cannot get everything. Maybe second trial, third trial, you can get the desirable peak. And from the peak only you have to do the analysis. So what is Lambert-Beer's law then? First of all, Beer's law, that is minus di dc equal to ki. That means this incident radiation is I, C is concentration. So minus di dc, that means absorption, that is concentration of the, due to this concentration variation, the absorption, it is minus means negative. That means inversely proportional. It is becoming, if you give more and more concentration, the absorption will become more and more. So the emitted radiation will be less, emitted light will be less, absorption will be more, emitted will be less. Quite natural. Now, from if you do the calculation and all, finally you get this relation I equal to I naught e to the minus kc. First order kinetics, that type of equation. Similarly, you have Lambert's law. This is Beer's law. I equal to I naught e to the minus kc. Similarly, you take di dt equal to ki. What is t? T is the thickness of the cuvette, the length, path length of the light, through which the sample thickness. Sample thickness I am talking about. Not concentration, but thickness. Then with that, you make another calculation, you get a relation.
So thickness of what?
Thickness of the cuvette. Sample. So I naught equal to I naught e to the minus kct if I combine the two. And from that, you get the relation I equal to I naught 10 to the power kct. So if you take log I naught by I is called absorbance. Not absorption, that is absorption. Now I am talking about absorbance. Absorbance is log of I naught by I. I naught is what? Incident light, and I is transmitted light. Passing through. The amount falling onto the material matter, and then how much is coming out.
Some amount is absorbed.
Some amount is absorbed, yes. So here A absorbance equal to log of I naught by I. If I put it here, so it will be A equal to KCT. Okay, these two things are there. C is there and T is there. These two parameters. So A equal to KCT. Now instead of K, we can use epsilon sometimes. K is a general term actually. Always you use K. That is too general. Now to make it specific, epsilon is used. Solvent, it depends on solvent. This epsilon value that depends on solvent. Suppose you make C equal to 1, you make T equal to 1. Then absorbance equal to epsilon. From that you can find out epsilon of a solvent. Okay. Now this instrumentation part I will skip because these things already I have discussed earlier, right? So that I can skip. Same thing is there here. So I am directly going to these things too much of details I don't need. This grating I wanted to show you once more. So this grating is what? What are the things I told you? One is collimator lens, that is focusing. After that prism. Prism is splitting the light into different patches or band of light wavelength, right? Band. So now every band, if you want to select, it will have to pass to a slit. Again it is passing through one slit. Maybe yellow color or maybe orange color. A particular one you are passing through some hole. That is called slit once again. Then this contains maybe 20 wavelengths. Out of the 20 wavelengths, one you have to select. That you are doing by grating. Grating doing what? Scattering this light in different directions. If you don't scatter, you cannot separate each and every individual wavelength one by one. So in the grating we are doing that. Separating these wavelengths into one by one. And just rotating the grating. Grating is a wheel. So it is rotating, machine is rotating that. Say particular wavelength is allowed to go through the slit, others are all blocked. So single wavelength you are sending to the solution. For analysis, passing a single wavelength is essential. Multiple wavelengths if you pass, you cannot understand anything. So that is the purpose of grating. This is the sample holder or cuvette, that's also I discussed earlier. So today I am skipping because these things are already discussed. So directly I am going to this single beam and double beam spectrophotometer. Single beam is one light is passing through first sample and then passing through solvent, and after that you have to take the difference of the two. So one by one you have to put the first you have to put into the cuvette into the machine and then take out and put again another one. One by one you have to do. So it is much more manual. Now there is a better one has come in the market, which is called double beam. Double beam means you have a reference as well as sample both together. You have two chambers, two cuvettes. In one cuvette you have the sample solution, another cuvette you have the solvent. Now same intensity, same wavelength of light is passing through both together at the same time. Then the difference is actually collected, difference of the two, and recorded. Okay, that's called double beam. Single beam, it is cheap. Is it construction? Is it to use and economical? But double beam, it has got lot of advantages. So nowadays, single beam is obsolete. Everyone is using double beam. Now applications. This is the most important part now for us. Application of invisible spectrophotometry. Detection of impurities, structural elucidation of organic compounds, structural analysis of organic compounds. These are all applications. These are actually the requirement. Effect of geometrical isomerism, cis trans, position cis trans, alkyl substitution, double bond, position of double bond, number of double bonds, conjugated or non-conjugated, lot of ideas we can get from invisible. Now coming to choice of solvent. Non-polar solvents are usually used. What are the solvents? So these are the solvents. Get a list of solvents. This acetonitrile solvent can be used. Wavelength of acetonitrile, you get a peak at 190. Okay, so if you know that you will get a peak at 190 due to solvent, so you can ignore that. And if you take one sample, another solution, a sample and solvent, then automatically this peak will be deducted. So there will be no noise. Understood? Now coming to Woodward-Fisher's rule, in brief I will discuss, not go much detail. This is called heteroannular dyne. Heteroannular dyne means two double bonds are there, but both the double bonds not in the same ring. Two double bonds are there, but both the double bonds are not in the same ring, though they are conjugated, but not in the same ring. That is called heteroannular dyne. For this type of molecule, we have a value, base value, it is called base value, 214 nanometer. Then alkyl substituents, how many alkyl substituents? You see carbon number, this carbon, this particular carbon, there is a double bond. So with respect to double bond, how many number of alkyl groups you have? This one, here it is 2, here it is 3, and here it is 4.
Base value means?
Huh?
Base value.
Base value means it is called thumb rule. Happen to be true. There is no scientific explanation behind it. That is found that if you have this type of ring, you are getting a peak always at around 240. Without any other substitution, anything, if you take only the heteroannular dyne, then it is giving a peak around 214. So that's why it is called thumb rule. When there is no real reason behind it, but it is found, that is called base value. So this is the base value. So how many number of substitution? 1, 2, 3 and 4 alkyl groups. This line is actually alkyl group. You can consider this is one alkyl group. So 4 alkyl groups are there because CH2 is there, na? CH2. So you can consider that is an alkyl group. So 4 alkyl groups are there for each and every substitution. 4 into 5, so 20. Exocyclic double bond. This is for this double bond is exocyclic. That's why it is 5 is added. So what will be the value? 239. Just add these values. Absorption maximum is found at 239. And more or less, this type of rule what we are making practically found almost matching. You take hundreds of compounds, almost is matching. Okay, that's why the Woodward-Fisher rule is important. You can predict that where you are supposed to get the peak. After that, you can do the real testing. Before doing the experiment, you can predict that where we are supposed to get the peak, and then you can go for the actual experimentation. This one is called homoannular dyne, where both the double bonds in the same ring. Here the base value is 253. For heteroannular it is 214, and for homoannular it is 253. Then alkyls, one thing I can tell you, if there is a beta resonance, shift is towards the blue, towards red, longer wavelength. If there is a conjugation, as I told already, if there is a conjugation, the shifting will be towards longer. So here, this conjugation is there, but it is not very effective. Both the double bonds in two different rings, so it is less effective compared to in single ring. It is homoannular, no? So both the double bonds in the same ring. So conjugation, extent of conjugation is better compared to the other one. Maybe because of that, here you are getting at a longer wavelength. Here you are getting 214, here you are getting 253. The reason behind it I am telling you. Here the extent of conjugation is not that effective compared to this. Here is better conjugation. So that's why shifting towards red. So 253. Alkyl substitutions numbering given 1, 2, 3, 4 numbering given. So 4 into 5. And exocyclic double bond. Exocyclic double bond means actually this is a ring. Try to understand exocyclic double bond. This is a ring. With respect to that, there is a double bond outside the ring. Follow me? This is the ring. With respect to that, there is a double bond outside the ring. That is exocyclic double bond. Here also there is another exocyclic double bond. So 2 exocyclic double bond is there. So that's why 2 into 5. So that's why total value, if you add, it is coming 283. So here it is 239, here it is 283. Quite different. These two are just example that of Woodward-Fisher rule. I'm not going into much detail.